Hello again. In this lecture, we're going to explore stacking and how to use NumPy's various functions to conduct it. These include stack, vstack, hstack, and dstack. Today, we'll show you how they differ and when to use each one. Let's begin by importing and displaying the two datasets we intend to use here. The first one is the basic one. Lending Company Data, Numeric. The second one is a version of Lending Company Data, Numeric, which has been modified to contain missing data. Make sure to also clean the dataset from the NaN file before moving on by creating a filler value and substituting all the NaNs with the said number, and then switching out every filler with the appropriate mean for the given column. We've already explained how and why we do this earlier in the section, so in the interest of time, we won't be going over this code again. Superb! Now that we have our datasets ready, let's get into the meat of it. Stacking is the act of placing multiple objects on top of one another to create a bigger object. When it comes to NumPy, we can just stack arrays of matching shapes to create a larger array that we can refer to as a stack. NumPy contains several functions for stacking, so we'll start with the most straightforward one, stack. We'll use it to create a new array from the first two columns of Lending Company Data, Numeric. We simply type np stack, and within the parentheses, we add a tuple with the two arrays we want to stack. We see a 2D array, where each row contains the values of the equivalent column of the original array. In fact, it's like we've sliced the first two columns of Lending Company Data Numeric and then flipped them sideways. Another way to think about this is by transposing only the first two columns of the original dataset. We can prove this by executing the NumPy's transpose function while using the first two columns of our dataset as an input. However, we stated that stacking allows us to place the values in whatever order we want, right? Let's see what happens when we switch the order of the indexes in the function. The new output now has the elements of the second column appear on top. Therefore, whatever array we place first is placed at the top of the new array, followed by the array we put second, and so on. Splendid! So, we just took two columns and transformed them into rows by stacking them on top of one another. However, we can just as easily stack them side by side and create a new array with two columns. Doing so depends solely on what axis we're using to stack these arrays. So just copy the code into a new cell and set the axis argument to 1. As you can see, the output is now an array with two columns rather than rows, which is exactly what we are trying to achieve. Great job! We also mentioned that we can stack multiple elements rather than two at a time. To do so, we just need to include another array in the tuple. For simplicity, we'll just add another column from Lending Company Data, Numeric. This appends the newly added column to the back of the array as we expected. Another peculiarity of stacking is that the arrays must be the same shape. To test this out, we can try to stack arrays which have the same number of rows, but not the same number of columns. For example, we can change the last array of the tuple to be a slice containing the first two columns. When we run the cell, we get a value error. Even though intuitively it makes sense that such arrays should be stackable, the bottom of the error message clearly states all input arrays must have the same shape. Thus, we need to keep this in mind when selecting the arrays we're trying to stack. Okay. At the beginning of the lecture, we mentioned there are several functions we can use to stack values. We already saw how stack works, so let's quickly examine vstack, hstack, and dstack. We'll be using these to stack two matrices, so let's quickly call the shape attributes of the following two arrays to verify that they have the same shape. We see that both arrays are 1043 by 6, so we can proceed with the functions. vstack is short for vertical stack, and as you can probably tell, the function stacks 2D arrays vertically. Hence, it places the first array on top of the second one, which results in a longer array. If we use vstack on the two datasets we imported, we can't outright tell what's going on based on the output, since we still have 6 columns on the screen. Therefore, to make sure we've stacked them correctly, we can call the shape attribute of the stacked array. The output reads 2086 by 6, which makes sense because each of the two datasets was 1043 rows by 6 columns. So we can confirm that these arrays were stacked on top of each other. Next up is hstack. The name is short for horizontal stack and stacks values horizontally. That said, if we horizontally stack the same two matrices, the result should be a wider array. To see it in action, we can go to the start of the line. Change the V to an H and remove the shape argument. We see a ... sign in every row, meaning this array contains more than 6 columns. Once again, to make sure we've stacked the arrays horizontally, we refer to the shape attribute of the output. The 1043 by 12 backs up our assumption that the two 1043 by 6 arrays were placed side by side, resulting in a wider stack. Lastly, let's check dstack. This one is a little different. The D here is short for depth because we stack arrays in the third dimension. Unlike vstack and hstack, dstack adds depth to the matrix, so it returns an array of a higher dimension than its input values. If we once again go to the beginning of the line, change the H to a D, and remove .shape, we'll see a very different output. Instead of having one 2D array on the screen, we have a 3D array consisting of multiple two-dimensional 6x2 arrays. It's good practice to once again check the shape of the output to figure out its structure. The outcome reads 1043 by 6 by 2, meaning there are a total of 1043 6x2 arrays, exactly one for each row of the initial datasets. Another way to think about it is that the first index of the stack is the row, the second index is the column, and the third is the original array we got the value from. To make sure we interpret the output of dstack correctly, let's call its first element. To do so, simply remove .shape and use indexing to express position 0. The new output is a 2x6 array, which consists of 2 columns with identical values. Each column contains the first row of either lending company data numeric or its NaN riddled version. Hence, the first index represents the row. Now, if we add a second index and also set it equal to 0, we'll get two identical outputs of 2000. So, the second index must refer to the columns of either input array. Lastly, we can add a comma, colon, between the two zeros. This ensures we're slicing all the columns with a row index 0 and a depth index 0. The output is the first row of the original dataset variable, lending company data numeric. That means the third index represents which array the values were pulled from. Superb! Earlier, we said dstack is a bit different. And that's because when we're working with 2D arrays, we can replicate its output with the stack function. To verify this, copy the dstack code from the last cell, remove the indexing, and rerun the cell. Now, if we switch to the stack function and set the axis argument to -1, we'll get the exact same output. Why? Because the stack function always returns an output that is exactly one dimension more than its inputs. Since dstack works along the so-called third axis, the two functions work identically for 1D and 2D arrays. However, this doesn't hold true for arrays of higher dimensions. If we have an array with 3 dimensions as an input of dstack, the output will be 3-dimensional. Nevertheless, if we use the same input for the stack function with axis -1, we'll get a 4D array. To test this, we'll quickly generate two 3D arrays of size 2 by 3 by 4. And call dstack, as well as stack, with the axis argument set to -1. As expected, we see different outcomes. If we quickly check the shapes of the two output arrays, we'll confirm that the dstack one is 3D, while the stack one, 4D. Hence, the two functions are only ever equivalent for inputs of up to 2 dimensions. Fantastic! Now that you've seen how stacking works, we can shift our focus to yet another way to manipulate data, called concatenating. In the next lecture, we'll learn what it is and how it works. Thanks for watching!